Hello student, we'll see differentiator using op-amp. This is ideal differentiator circuit. In differentiator circuit, this R1 is replaced with C1. If I'll apply KCL over here, as per the KCL, it says incoming current is equal to outgoing current. So IC is equal to IF plus IB. But we know this is IB is equal to 0 because why? Because the input impedance of this ideal op-amp is equal to infinite. So that's why IC is equal to IF. We know the current across this capacitor, which is equal to C into dVc by dt. But the voltage drop across this capacitor is equal to V minus V2. So what I'll do, I'll substitute Vc into above integration equation. This current IF, which is flowing through this feedback resistor, which is also equal to V2 minus Vout divided by RF resistor. Now I'll equate this both the equation. I'll get C1 derivative of V in minus V2 is equal to V2 minus V0 divided by RF. We know the R1 is connected to ground. So because of virtual ground concept, this V2 will be ground. So this V2 will get cancelled. This V2 will get cancelled and I'll get equation V out is equal to minus C1 RF into derivative of input voltage. This RCOM resistor is connected from non-inverting terminal to the ground, which provide the bias compensation. This output voltage of a differentiator, if I'll give sine wave and corresponding to this sine wave, it will give inverse cosine wave. So the input voltage is V sine omega t, the output will be inverse cosine. If I'll give square wave, which is actually made up of many step signals, so we have the extend the same principle as we use in step input, will get spikes corresponding to a rising and a falling edge. You can see over here at the rising edge will get falling edge spikes, and at this falling edge will get rising edge, because there is 180-degree phase shift between the input and output. This minus sign will indicate this. If the input is positive, then the output is negative. The output voltage is equal to rate of change of input voltage with respect to time. So if the Vin is equal to input amplitude voltage, amplitude A, will get output will be the integration of this, or we can say minus A. That's why the output voltage is 0 when the input voltage is at the constant A. There is some problems associated with ideal differentiator. The gain of this basic differentiator is equal to Rf upon R1. The R1 is nothing but your capacitor reactance, which is equal to Xc1. As reactance decreases with increase in frequency, so the gain will increase with increase in frequency. The input impedance, which is equal to Xc1, is reduced with increase in frequency. This will make the circuit much susceptible to high frequency noise, which will make the amplified noise at the output can be completely override the output signal. So at the output of op-amp will get amplified version of noise only. This noise will suppress the actual input signal. So for that they did some modification, which is nothing but practical differentiator. So they introduced the resistor in series with this capacitor, and one capacitor will in parallel with feedback resistor. This both instability and the high frequency noise problem can be reduced or corrected using this practical differentiator. These two components R1 and RCF is introduced for this basic differentiator circuit. Due to reduction in this reactance, capacitor reactance at high frequency, the gain of this basic differentiator is increased drastically. To stabilize this, they introduce one resistor is in series with capacitor. This R1 will control the amount of increase in the gain at high frequency. And this RCOM also introduced for this bias compensation. The differentiators are used in PID controller as high pass filter. This differentiator is used in wave shaping circuits to generate narrow pulses, which is corresponding to any shape changes in input signal. Thank you, student.